great. Thank you. So today we are very excited to have Dr. Jennifer Ngadiuba to give us the A3D3 seminar. So Jennifer is an associate scientist and Wilson Fellow at Fermi Lab, specializing in the application of AI for particle physics. So her innovative research focuses on real-time data analysis techniques and model-agnostic search for physics beyond the standard model as LHC and the CMS experiments. So Ngadiuba's contribution have earned her several accolades, including the 2024 IUPAP C11 Early Career Scientist Prize and the U.S. Department of Energy's AI for HAP Award. With a background from institutions including like CERN and Caltech, she is at the forefront of integrating AI technologies into particle physics, enhancing data processing and analysis capability for future discoveries. So I will let Jennifer take it away. Jennifer, please go ahead.
Thank you very much for the introduction, and thanks a lot for the invitation. Yeah, I'm Jennifer, and I'm part of the CMS experiment at the Large Hadron Collider. So we'll talk today about the application of machine learning-based anomaly detection at the LHC, from offline data analysis to also the application to real-time systems. The beginning of this century marked a big expansion of our knowledge of the universe from the very small to the very large scale. We had major discovery in the last decades from the discovery of the Higgs boson at the Large Hadron Collider in 2012, which completed the standard model of particle physics, to the discovery or measurement of gravitational waves, which confirmed the theory of general relativity. However, we're left with fundamental questions about the universe. The standard model doesn't account for neutrino masses, gravity is not included in the theory, or the standard model of particle physics explains only 5% of the universe. In fact, there is no standard model candidate for dark matter. And also doesn't account for matter-antimatter asymmetry, which explains why we see the universe as it is today. So to answer to these fundamental questions about the universe, we have to probe the fundamental structure of nature. And to do so, we build complex experimental devices, large infrastructures made of big collaborations. From the Large Hadron Collider, which will be upgraded in the future to more powerful high luminosity machine, to the design of future colliders, to like the design and production of high intensity neutrino experiment. So this is becoming, the experiments are becoming even more sophisticated in the near future. So with this comes also increasingly complex data, both in volume and dimensionality, and so an increasing need to develop methods for efficient and accurate data processing. So these, I think you cannot see my mouse. Okay. So this plot on the top right shows the streaming data rates in bytes per second as a function of the latency requirement. And we compare here different particle physics experiments with the industry standard. And you can see how the particle physics experiments are extremely challenging in terms of the data volume, but also latency and data rates. So this brings challenges in simulating expectations for what experiments may observe, but also it brings the need to develop innovative data and discovery-driven approaches for physics analysis. So in this picture, certainly the LHC represents some of the most interesting challenges in terms of big data. In fact, the LHC, we collide proton beams at an enormous frequency of 40 megahertz. And these are collided in 4 different places along the ring, which we call interaction points. And each collision produces thousands of particles. And in order to reconstruct each of these particles, we build these complex detectors at each of these interaction points, which are high granular. So for example, this is a schematic of the compact muon solenoid. So the CMS experiment, which I'm part of, And these detectors have like up to 1 billion readout channels, which are used to detect these particles and to reconstruct them, so to reconstruct the actual proton-proton interaction. So given these numbers, we expect, or we have actually extreme data rates of a petabyte per second. At the same time, collisions that produce interesting products, for example, an Higgs boson, are typically very rare. So this shows the production probability for many different standard model processes. And you can see, for example, that the probability of producing a Higgs boson is 5 to 9 orders of magnitude smaller than producing only backgrounds made of jets. So we expect the new physics to be even more rare than this. Which also means that we don't need to keep all the events, as the majority are, let's say, not interesting. So we have a data reduction workflow in place where we filter data or events through multiple stages. The first stage, what we call the level 1 trigger, absorbs like petabit per second of data coming out of the detector, and needs to make a reconstruction and a decision if to keep the event or not in just a few microseconds, because this is the latency that we have based on the on-detector buffer, so the time that the detector can actually keep the data before it discards them. So because of this strict latency and high rates, the algorithms here are implemented on FPGAs or custom electronics. And this level of filtering brings down the rates to tens of terabit per second. Then finally, the rates are low enough to process them through CPU or commercial CPU or GPU farms in the 100 milliseconds latency, which is still pretty strict, to bring down the rate down to tens of gigabit per second. So these are the data that we finally store and process offline through a worldwide computing grid, such that at the end, after filtering, we make physics discoveries with like 0.0025% of the events, while the rest is lost. So this works well when we know what to search for example, the Higgs boson or some motivated BSM theories, beyond standard model theories for new physics. So these plots actually show a huge amount of new physics theoretical scenarios that we're probing at the LHC, and there are many. And every time, like let's say we probe one BSM theory, we make an analysis. And this works well when you have indeed all these theoretical guidance, or let's say you have strong physics assumptions, such that you can use them to guide each step of the data analysis workflow, from the data reduction to the data preprocessing to the final construction, so the construction of the final, let's say, high-level features that you use to do some final statistical interpretation of your analysis and set, for example, limits on these theoretical models. However, nature might be different from all of these theories. So it might be that we're not looking in the right corner because we might not have imagined yet how new physics look like. So imagine if like maybe there is a theoretical model which we haven't thought of, and so that we're not covering it with these searches which are very tailored. So we started thinking about new approaches in which we, let's say, go back looking at data with no signal hypothesis in mind, and eventually remain surprised, or hopefully remain surprised, in a way that you can identify an anomalous signal and then formulate an alternative hypothesis, which you can test then with new data and more traditional techniques. This is what we call anomaly detection. Today we can implement anomaly detection efficiently with AI. In fact, now we have a lot of experience in using machine learning in particle physics, which can be dated back to the 80s. Although, of course, we were using mostly shallow networks back then. But then over the last decade, there was like a rapid progress guided by technological breakthrough, which led to a revolution in this area. So now machine learning is well embedded in particle physics. So how do we want to use AI for, let's say, to implement a data-driven search strategy, which, as I said, we call it anomaly detection. So the main idea is that you want, of course, to identify some rare events in some data sets. So these rare events are BSM physics, so we expect them to be rare. And of course, they deviate significantly from the standard model, which is what basically make the majority of the data. So expect these anomalies to not conform with the standard model, and so not with this normal behavior. So eventually you can just learn the normal behavior through a neural network in a way that you learn the standard model background, and everything that deviates from it could be some potential new physics. So we can apply this idea, we started applying this idea to the search for digit resonances, which will be clear in the moment. So first of all, jets are spray of hadrons initiated by a fundamental particle of some kind. It can be gluon or light quarks or standard model heavy bosons, like the WZ, the Higgs, or the top quark. So these spray of hadrons are then clustered into one object with some jet clustering algorithm. And what is interesting is that by analyzing this object, you can identify different properties which are different depending on the mother particle. So what we do is called jet tagging, which is basically the analysis of the structure of this jet to identify the mother particle. So in order to have, before you have the jet, you actually have to reconstruct these particles one by one. That's what we do at the LHC. And just like to take an interlude, this is done typically by combining many different detectors in order to make up these particles. This is what we call the particle flow algorithm. So here you see, for example, a schematic of the compact muon solenoid. We have many different detectors. So going from inside out, we have the silicon tracker, which reconstruct indeed the tracks. Then you have the calorimeters, which can reconstruct electrons and photons. The hadronic calorimeter reconstruct hadrons. And then outside of superconductive solenoid, which makes like a strong magnetic field, we have the muon detectors. So in this way, you can reconstruct all the electromagnetic particles one by one, so you know which one they are. So you say, like, if there was mostly electromagnetic calorimeter energy, that's a photon, or if there was electromagnetic energy plus a track, that's an electron, and so on and so forth. So we can really reconstruct them one by one. And after we do that, we combine them into the jet clustering algorithm and make jets. So characterizing these jets is a key task at the LHC because it allows us to, it's a probe, say, for new physics, but also to make more precise standard model measurements or X-related measurements. So for example, you can have a new particle like a graviton or a radion decaying into W bosons, which then hadronize and make like two jets. And so by knowing that the jet is a W, then you can actually infer the mother particle, which could be a new particle. So, however, indeed, to know like what's the mother particle of the jets, you need to analyze these characteristics, and we exploit them to suppress indeed this abundant contamination from background jets, which are not interesting. These are particularly the jets from single quark or gluon. And we expect them, for example, as you can see in this cartoon, these background jets to have like a kind of a single structure after you cluster, and signal jets instead to have multiple structures, so which can be like two, let's say, energy structures, or three, depending which particle it comes from. Or also sometimes we actually expect jets to be very displaced in the tracker, so in the inner part of the detector, if there is some long-lived particle inside, for example, a bottom quark. So you can really exploit like all these characteristics to figure out if this jet comes from an interesting particle. So there are many different examples of jet substructure observables that we typically use in standard analysis. This is like the jet mass, or this called dense objectiness. But just looking briefly at these plots, you can see that there are very different characteristics between signal and background. So in principle, you could just apply some selections and to isolate your signal and reduce the background. But the point is that you need to know what your signal is. Well, instead with anomaly detection, we wanted to generalize. So basically, learn only the background and remove that. So in the usual analysis, indeed, we use this, let's say, standard just substructure observables because you are searching for particle A, which is some unknown new particle, which decays into two particles, B and C, which you expect typically to be standard model particles. So you already know, which selections to apply to identify these jets. So in a normal search, what you do is you first look if there are two jets in the collision event. Then you look if these two jets are consistent with a heavy standard model particle. And if so, you then reconstruct the invariant mass and you reconstruct the invariant mass and then look if there is a bump on the top of a smoothly falling standard model background, which can be compatible with the hypothesis of a new resonance decaying into two jets. We've done this with this process. We applied this process in a lot of searches at colliders in which we tried, let's say, or we tag these two jets by, let's say, knowing what the particle we're expecting in the final state. However, there are many other possible BSM scenarios that are not covered by, let's say, these dedicated searches. Or there could be a BSM signal we never thought of. So this is a natural place to explore novel analysis strategies because indeed we have done a lot of this. We understand jets in some sense. So how do we generalize? So instead of applying some selections that identify B and C as some unknown particle, we train our network to learn only the background in some control region. And then we tag each jet as anomalous in the signal region with no assumption on how it looks like. So from going to that to an actual search, there is, many different things that we do, but they're actually, the workflow is the same as standard analysis. You make a selection on some metric, which in this case, it's an anomaly metric. Apply selection, identify your signal region, and then make this bump hunt in which you search for a bump. However, in this case, with respect to standard searches, that we have a lot of machine learning engineering that go into what's the best machine learning method that we can use that gives us the best, most sensitive anomaly metric. So there are many different ways in which this metric can be constructed based on some different methods. And these methods, we say that they can have different, let's say, model dependence. For example, you could just learn to understand regular jets and look for outliers. And this is what we call unsupervised learning. There have been, in the past years, 2 atlas searches using these methods to boost searching for resonances in 2 jets, or also in lepton plus jet and photon plus jet. And just to understand a little bit how this can be implemented, this can actually be implemented through autoencoders. Autoencoders are this decompression algorithm in which you take some high-dimensional input data, compress them into low-dimensional latent space, and then try to reconstruct the original data from this latent space. So yeah, you want to basically minimize the reconstruction or the difference between the input data and the reconstructed data, and that's your loss function, which is basically a mean squared error. So if you train these on background, it will learn to reconstruct this background, and then when you try it on a different, on new data, which contain, for example, some BSM physics, the reconstruction will fail, and so it will give a high mean squared error. In fact, we started thinking about this a few years ago to use this method to define a background jet veto. So exactly to isolate more anomalous events, which cannot be reconstructed by the autoencoder. These are some of the first works. So you can see here on the bottom right, this is the reconstruction error. So this MSc for QCD, so for background jets in gray, and the new signal jets in orange and blue, which the network has never seen. So they give really a high reconstruction error. So you can apply selection there to isolate these anomalous jets. There's also variation or like a different flavor of autoencoders, which we call variational autoencoders, in which instead of encoding an input as some single points, you encode them as a distribution over the latent space. Typically, this distribution is chosen to be normal. So this is basically used as a regularization of the latent space in which you have like Gaussians, which gives like, let's say, a more informative latent space that, as you will see later, can be used. It can be used to isolate anomalies. So I do apply this to digit search because now we have a tagger per jet, but at the end we were looking for two jets. So for example, you can train a jet autoencoder on each jet individually in observed, let's say, digit data. So the ones that we actually collect. And you have to do it in a region where you expect very little signal. So in a region which is enriched in background. So that's what we do. We select this region, we train the model, we get a loss per jet. And at that point, you want to combine these two jet losses, for example, the minimum of the two, and apply these to the signal region. So like this, you can go from anomalous jets to anomalous digit events, combining these two individual losses. What we observe is that you typically have a high dependence from the loss, the combined loss, whatever you choose this to be by some optimization, with respect to the digit invariant mass, which we would like to be smooth because we're looking for bumps there. So if you just apply some flat cuts on these loss, you will get like some sculpting of your background distribution, as you can see here on the right. And we don't like that because this is difficult to model at the end. And also might create, some sculpture, some like, fake bumps, things like that. So what we do instead is that after, let's say, we plot this, we also train our network to regress quantiles corresponding to fixed efficiencies. So basically what we obtain is like a smooth cut threshold, let's say, that moves together with the digit invariant mass. And like this, we obtain a very smooth digit invariant mass distribution. So another way of doing anomaly detection is through weakly supervised learning. This increases the model dependence. Let me explain a little bit how we apply this. So typically in a fully supervised strategy, you train on pure Monte Carlo signal and background. So you have these like two samples that you are labeled, they're labeled very well, and you train a network to distinguish them. And you have to use Monte Carlo, simulation to do that, because that's where you get the true labels. However, true labels are not available in real data. So you can instead think of constructing two samples made of noisy labels, which have different purities, which you expect one sample to be enriched in background with some small signal contamination, another one enriched in signal with some background contamination. And then you train a neural network classifier on these two samples as you would do for fully supervised. And you expect that if these samples are constructed properly, then you learn actually to distinguish signal versus background. And in fact, the higher is the signal fraction, the better the classifier, the better are the classifier performance. However, here you have to put some model dependence because you need to make some assumption on these different purities. So you need to know where you expect your signal to be. So we do this by considering the fact that we're looking for bumps, for very narrow resonances, which means that you expect your signal to be confined in a small window in the digit invariant mass. So you can choose. You don't know the mass, of course, of this signal, but you can actually make a scan. So you make these windows in which you expect the signal to be confined in a small window, and then the background has to be on the sides of this. So that's your background rich sample, and the small windows is your signal rich sample. And then you train our network classifier as usual on this and define some anomaly score. The cumbersome part here is that indeed, since you don't know the mass of this hypothetical signal, you need to do so many sliding windows in order to cover the full mass range. There are other methods that we explore to construct these mixed samples, and I'm not going through all the details, but I'm just saying that some of them can be like more or less sensitive to this process. So there was actually one Atlas search, so Atlas data detector, using the Koala method for the boosted digit phenastate, which came out a few years ago. But in this talk, I will mostly discuss the most recent results from CMS. So finally, we talked about unsupervised, weak supervised, but there is also one other method that we're exploring, which is more like what we call semi-supervised. The idea is that this is an hybrid approach between model-independent and standard search. The idea is that you encode some prior knowledge of how a potential signal could look. This is obtained by training a density estimator on a mixture of simulated signals that you expect to look a little bit like the signal that you are searching for. And on top of that, you also train an additional density estimator on the background simulation. And once you have these, like, let's say, these two density estimators, you can construct the 2D space of the two loss functions. So on the y-axis for signal, on the x-axis for background. So you expect the signal to score high on the background loss and the background to score high on the signal loss. So you can actually like put a selection, 2D selection here to basically catch your hypothetical signal. And if your true signal is very close to the hypothetical signal, then you imagine that you can catch also a lot of it. You can also make this even more signal specific, of course, if you, if you inject the actual signal that you're looking for. So this year, CMS came out with these results in which we presented the first CMS search for anomalous digit resonances using these novel machine learning techniques. And the cool thing is that we try all of these methods in one analysis. So there was like a lot of work like to synchronize among them because it was many different teams working on it. But we can look a little bit more into it. So particular, so we try all these methods. These methods are very different in construction, but also they use different input features. With the autoencoder using like the minimum amount of information with really no, let's say, model assumptions. And the others instead using like also high-level features. So when you use high-level features, you're kind of like already injecting some, let's say, bias into what you're searching for. We probe also a lot of different models. So because the main idea of anomaly detection here is that we want to generalize to as many signals as possible into one analysis. So we generated many different combinations of the resonance A and the mass of the resonance A's, and the mass and characteristics, internal characteristics of the B and C particles in which the particle A decays. So like this, we can try to understand how really what is the generalization power of these methods. So we see, first of all, that when looking at the correlation matrices between the different methods for different signals and also for the background, we see that the approaches are very complementary because, in fact, they agree partially on real anomalies, but also in different degrees, depending on the signal. There are some high correlations sometimes seen here because some methods are way more similar than others, but otherwise, like, the correlation is rather minimal, meaning that they're very complementary. What is interesting is that we tried first to understand indeed what's the generalization power and what is the discovery power of these methods with respect to standard searches. So to do that, we inject a signal of a varying cross-section. So the cross-section is a measure of, let's say, the production probability. So we inject this signal in the background simulation, and then we calculate the p-value. The p-value for us is like a measure of how likely it is that you can discover this particle. And then we compare among all the different methods. And in particular, for us, like there is this discovery threshold, which is the 5 sigma. And above that, you're basically claiming a discovery. And you can see basically that the anomaly detection methods can claim discovery way before any other traditional digest search or dedicated search for some signal. So which means that the process can be way rare, can be really, really rare, and anomaly detection would actually find it way before you actually make a dedicated search for it. So all anomaly detection methods in general improve the sensitivity with respect to traditional methods. We see this also for another type of signal. So sorry, here it was like a 2-pronged signal. This is like a 3-pronged signal. Whether we see different, let's say, performance for the different methods, because indeed they are complementary. So you don't expect them to be the same for every possible signal. But in general, what is important is that we always like improve with respect to traditional search. So then we don't see any new physics, but so that we perform this bump hunt on the digest invariant mass spectrum after we select on this anomaly score. So these are like all the possible, let's say, spectra that we fit to look for a bump. We don't see any, unfortunately, and I mean, there are some discontinuity here because indeed, as I said before, the weakly supervised methods have to do this sliding window approach. Finally, said that, I want to mention, so this is all applied offline. The question though is like, we're looking for anomalies offline. So after we have placed this data reduction workflow, in which like 99% or more of the events are rejected. So the question is, if the new physics is even in this offline data, given that event filtering starts very early in the data processing. So we started thinking about addressing the challenge as early as possible in this data reduction workflow, and in particular in the hardware trigger, so the first level of filtering. However, how do you put neural networks here can be like challenging, because neural networks can become relatively large, or methods can become, you know, like not let's say hardware friendly. And so I expect the memory and number of operations required for the inference to easily explode. Well, instead we have strict constraints in the hardware trigger. We need to meet latency constraints of a few microseconds, implement them on FPGA, and also have scarce resources because most of the, let's say, FPGA farm is occupied to do a lot of other things, like calibrate sensors, build physics objects, and so on. So to achieve this, we use, to fit a neural network here, we use HLS for ML, which I'm sure like people in this crowd are familiar with. It's a tool that we started working on years ago to efficiently program the FPGA hardware for neural networks with experimental constraints in mind. To start from, it converts like your machine learning model into FPGA firmware through a highly optimized code written in high-level synthesis, which allows you as a user to indeed meet the constraints that your experiment might have. So just like to recap how, let's say, what we have to do to like indeed, meet the constraints of the experiment. I want to remind you that the neural network inference is mostly matrix multiplication. And this can be implemented efficiently on FPGA using digital signal processors. However, there are a limited amount of these DSPs, more than FPGAs, so you can imagine you can't like fit like the biggest neural network that you would like to, or you can, but playing some tricks. So, for example, you can apply compression and pruning to remove the connections that play a little role for final decision. So basically zeroing some multiplications, and which also means less operations, and so less DSPs used or resources used on the FPGA. You also apply quantization, which consists of representing numbers with the fewer bits to reduce the resources used on the chip. So you training floating point, you can train floating point and then apply quantization after, so reducing these bits. Although, like as you can see in this plot, you expect at some point to lose some performance the lower you go in number of bits, because you're basically truncating your operations. And also, there are ways in which you can optimize the number of resources versus, let's say, the latency by changing the degree of parallelization of your operations. Yeah, so as I said, though, when you do quantization, you can easily lose accuracy when you go down to a certain number of bits. But instead, at some point, we started looking into quantization aware training, where you can specify the quantization while you look for the minimum. And the effect can be seen here on the top right, in which if you do post-training quantization, you lose accuracy very, let's say, at some number of bits. But if you instead do quantization aware training, you can keep the accuracy pretty high, down to really a few bits. So we started this some years ago by partnering with Google, that had this quantization aware training tool called QKRAS, which was then integrated in HLS for ML, so to squeeze the best performances or efficiency from your neural network inference when applied to very tight experimental constraints. There are also other ways of doing quantization. In particular, we would like to squeeze even more neural network inference performance when each parameter in the network may have its unique bit width. So in particular, with QKRAS, you optimize in predefined structures. So for example, you have one quantization set per layer, and the bit width is not part of the optimization. So which means that if you want to find the best optimization, the best quantization for your particular application, you need to run your own hyperparameter scan. Instead, what the wish it would be to optimize the bit width of each parameter of the neural network alongside the neural network accuracy. And this can be done through gradient descent. So this is like one of our latest work from a student from Caltech, who found a solution to this problem, which you treat the bit width as continuous variables, and then introduce surrogate gradients for discrete variables such as bit width, which allow you indeed to do this gradient descent. And also, he introduced a novel on-chip resource consumption metric that you can use to penalize the loss function for larger bit width. What's also interesting of this approach is that pruning is integrated naturally, because some weights are just sent to zero bits in some sense. So these are the results. You can see like basically how this tool can allow you for higher accuracy than QKRAS, or for similar accuracy but at way lower resources. So we want now, going back to anomaly detection, we now have the tools. So we know why we want to do anomaly detection. We know why we want to do it online, and we have the tools to do it. So let's put the things together, and then so that's what we try to do in CMS. This is a schematics of how the CMS trigger system works in the current data taking. As I said before, the detector is made like to reconstruct every single particle. And we do kind of the same in the trigger, but at a coarser level. I mean, a way less detailed level, because indeed you don't have the latency to do like a full, complete reconstruction. But still something that works pretty good. So you have the muon detectors that produce muons, and the calorimeters that produce like calorimeter objects, so like jets, electron and photons, taus, some energy sums. And then these objects are sent to the global trigger. The global trigger is where you can actually do a full event level analysis. For example, how many muons or how many jets and with which energy and so on. And in fact, there are many different algorithms or event level filtering algorithms that are in the global trigger. So this is like a screenshot of some of them, in which, for example, you require the existence of one muon with a certain energy, or two muons with a certain energy, or some jets, and so on. Though the latency is very, very tight, we have 4.2 microseconds to do all these, and most of the time is spent basically by the muon detectors and the calorimeters to produce indeed these basic physics objects. So, of course, we started thinking about using these, say, event level information to make an anomaly detection, so checking if the event is anomalous with respect to some background. So we did this, we started looking at this using autoencoders, which is like the most, the simplest way in given the latency constraints. We trained these on biased data collected by CMS in 2023 at 13.6 TeV. So in a way that you learn to reconstruct the average collision event. So you don't apply any filtering, you just apply to whatever comes from the collisions. And we expect indeed to use this to select, anomalous events. We use actually variational autoencoders because if you use variational autoencoders, you can actually define your metric in the latent space. You don't have to wait for the reconstruction. So this allows you basically to cut the network enough, and so the latency enough. And we use quantization-aware training with QKeras, we use FPGA resources, and then use HLS4ML to translate into firmware. So this algorithm is called Axolotl, Anomaly Extraction Online Level 1 Trigger Algorithm. It runs in 15 seconds, use very little resources, and you can see here like the space occupied on chip by it, which is the purple. The rest is occupied by other things that the chip has to do. So this plot shows the score. This is anomaly score. We can apply many different thresholds depending on which rate we are allowed to keep based on CMS choices. In fact, before we put it online, we tested it on a chip, or say on a system that was a replica of the actual system, so that we can look at the rates for different thresholds without really taking data. So that was the first test which was conducted in 2023. And this shows indeed the rates versus time for different anomaly scores, which give different rates. Then after that test, we finally put it online in spring this year. This plot here shows that most of the events triggered by Axolotl are pure, meaning that they're not triggered by the level 1, by the standard menu, so which gives nice complementarity. We have many different thresholds, as I said, and in particular, we have 300 Hz, which are sent to the scouting system, which makes let's say, lightweight reconstruction with respect instead to the actual, let's say, production system. And this is like a display of the most anomalous event in 2023, which looks very high multiplicity. Finally, I wanted to mention that we expect indeed the LHC to upgrade in the next years to high luminosity LHC, which will bring a more intense beam, and which basically brings way more interactions per bunch crossing. So today it looks, let's say, crowded at 60 collisions per bunch crossing. At the high luminosity LHC in 2030, we expect 200 collisions per bunch crossing. So way more crowded event. So CMS, but also Atlas, is upgrading the level 1 trigger and also the high level trigger to enable the same physics program we're doing now. So we expect indeed a more powerful compute, in particular, like we expect more, let's say, more latency, 12.5 microseconds instead of 4, 12 microseconds instead of 4. We expect new chips, and also we are able to do the full particle reconstruction for the new system. And so we expect also machine learning to be well embedded into the trigger to exploit all these new features. And in particular, we have now currently in CMS around 20 projects in development, accounting for 25 billion machine learning inferences per second. However, like considering what we're having now, which is Accelerator, and the future, there are still like a lot of challenges. In particular, when you start having machine learning embedded like in all the possible subsystems, you need some fast multimodal simultaneous training, because like what's downstream affects what's upstream, and so you want to do this fast. And we know that even for just one algorithm, which is an accelerator, there are so many steps that we have to go through to put it in production. The training, and then the synthesis with HS4ML, then you have to put it in the actual production chip with other stuff. You have to do the emulator, monitor the rates, and so on. So we're looking into automatizing these workflows and also allow for more bookkeeping, because you expect actually the conditions to change quite often. So you need to retrain often. So this has to be like fast, and also like you need to make sure that you version everything. So this is what we call MLOps, and there is work ongoing in this direction. However, I think there is also a wish of allowing at training time more robustness versus condition. This can be done, for example, through continual learning or reinforcement learning. This plot on the right shows an example that, let's say, method that was studied in CMS to do continual learning in a way that you basically do some top-up trainings when after a while, when your detector is degrading, and this allows you to recover the performance. Also, some of the wishes or things that we're looking into is like to explore transformers or more expensive self-supervised learning strategies, which can be implemented either on the hardware that we have now to manage, or like on new hardware like AI engines or novel distributed computing strategies. So this brings me to my slide. I want to say that some of these challenges were studying them, or like approaching them through this project called the Next Generation Triggers at CERN. Which happened thanks to the Schmidt Futures Foundation that gave CERN money to enhance the physics reach of the Atlas and CMX experiments at the University LHC and beyond by doing R&D and deploying novel technologies. There is a lot ongoing here. Much of them is very related to what I talked about, and you can also look at the page here to understand like everything that is going on there. And also, like, you can feel free to contact some of the task leaders if you're interested in participating or in hearing about let's say new job openings. So thank you.
Okay, thanks, Jennifer, for the great talk. So let's see, do we have any questions from the audience? If you have a question, please raise your hand or directly speak up, either way you prefer. Yeah, I have a question actually. So I'm sorry if it's a naive question because I'm not from this field. But I'm also interested in the scouting system, and I'm wondering if you could explain that a little bit more, and also how does it kind of interact with the anomaly detection work that you mentioned.
The scouting system.
Yeah.
Let me see. Maybe.
I think you briefly mentioned it on one of the slides.
Oh yeah, sorry. I think maybe I have one slide about it. Let me check. No, actually I don't. Okay, yes, so we do have two scouting systems. So there is the level 1 scouting system, which you acquire everything at 40 megahertz. But you acquire only the level 1 objects where the reconstruction is coarse, let's say. It's not the same as offline. And but in the future for Anomaly LHC, you expect to also, let's say, acquire all level 1 particles, level 1 reconstructed particles. But that's a lot of data. So we're looking into ways of doing compression. So either intelligent compressions, like through autoencoders, or some self-supervised strategy. So to reduce basically the bandwidth by, at least a factor of 10. Or you need to apply some selections. But that goes against the idea of the level 1 scouting system, because if you start applying selections, then it's not unbiased. Let's say you don't save everything anymore. So in principle, you could do some loose anomaly detection trigger in the level 1 scouting and only take those, or you use unsupervised learning or self-supervised learning strategies to do compression.
Okay, so, very nice. Thanks for the explanation. Do we have any other questions?
Yeah, I was going to ask one question. And Jen, yeah, great talk as always. Yeah, I was actually wondering that really high multiplicity event you showed is the highest anomaly score. Is it really true that CMS would not save that kind of event? I mean, I'm just thinking it might be. I'm just trying to think one of the first things my postdoc did, like here at Illinois, my first postdoc, like one of the first things we did, we worked on what's called the debug stream in Atlas, where like something with a huge number of tracks was written off to the side to understand why that is, and it was like a really, really weird event. And micro black holes could have like a very uniform set of particles and a very high multiplicity. So we had like this debug stream that we did partial event reconstruction. We kind of just wrote it off to the side to debug, to figure out what happened. I was just wondering, an event like that has, I don't know, many, many, many thousands of tracks, and is it true that would never get saved? Or do you like have some like means to save events that are really weird with lots of tracks and stuff outside of Oxalata? Just like, so this event really would have never been saved. Let's say you had like, a huge multiplicity. Are these saved by some other means in CMS, or are they just, this is really newly saved data that would have dropped on the floor otherwise?
So it's actually, I mean, they might be saved though through very heavy prescale. You know what I mean?
Yeah, I know what yeah, so you're saying it wouldn't store every of these, but there might be like, a set of really weird events that get like prescaled off and written for later.
Yeah, exactly. Yeah. So yeah, this is like the most anomalous event we found in 2023 that was not triggered by the unprescaled triggers. So we didn't look at all the prescaled ones. Might be like there are the prescaled ones as well.
Right, but they're still prescaled. That's the problem. Is they're only every so many get stored. Okay. Yeah, I figured you meant the main trigger, but like we have some just like really weird stuff. We have like a weird stream. Things are just put off to the side to try to debug. Yeah, interesting. So what is this event?
We're also debugging ourselves. Huh?
What is this event then?
This event looks like a pileup. Very much to me, unless I don't know physics, but looks very much like pileup. I must say that for this version that we have some preliminary results out, we had quite a high dependence from pileup. So like you could actually see the rates like skyrocketing with pileup, and which look more anomalous eventually because they have high multiplicity. Doesn't mean that there is no new physics there, but we're looking into mitigating, like for the new model that is now online, we're looking into mitigating this type of effects.
Great. Yeah, no, once you have these very weird events, you can, if they're high pileup tails, then you can like, there are methods you could do offline that the trigger would have a hard time. They could really try to like, disentangle any possible new physics from beam pileup and things. So this is awesome. So you're going to basically I think you have like a few hundred events or a few thousand events. It looks like the integral. You're going to come out with like a classification of these high Oxalata score events.
Yeah, so consider with this was like really the first run. It's like 0.5 inverse femtobarn. And by now we have like more like almost 100 inverse femtobarn. And now we're looking really into doing like full statistical interpretation of the data set. So
Okay, thank you. That'll be exciting. That's all I have.
Yeah, thanks. Yeah, that's very exciting too. I definitely agree. So do we have any other questions from the audience? Okay, if there's no more question, I would like to thank our speaker again for the great talk. So thank you, Jennifer, for giving us the seminar today. So we will.
Thank you very much for the invitation.
We will stop here. Yeah.
Thank you.